Let's get started. So today, talking about classifiers, basically just building on the last lecture on classification. So we'll actually go into building our own classifier. Well, we technically did that last time with that classifier where it was like based on the thresholds. But today we're going to do a different classifier called nearest neighbors. And that's going to be kind of the main classifier that we cover in this class. So a few announcements before we start. So all office hours, discussion, lab, tutoring sections all canceled next week because of Thanksgiving. As I mentioned last time, homework 11's due Saturday, turn in today for bonus point. Project 3 checkpoint also due Saturday. And the entire project's due on Friday, December 4th. And then homework 12 is out now as well. That's due on Friday, December 4th as well. So that's your last homework. So almost at the end of the semester. And yeah, so let's talk about classifiers today. So we're mainly going to be focusing our attention on the nearest neighbor classifier. So we kind of introduced this last time. We didn't really go over specifically what nearest neighbor classifier is, but intuitively that's what you guys did. So like I showed you that scatter plot of those points. I put my cursor somewhere and then you guys guessed, what the class is. Like, is it 0 or 1 based on what things look like around the cursor. So you guys are intuitively already doing a nearest neighbor classifier. So specifically what a nearest neighbor classifier does is it specifically looks at a certain number of nearby examples. So you specify that beforehand. So like it's usually called K nearest neighbors. So K equals the number of neighbors you're going to look at basically. So if K equals 3, what you're going to do is if you pick a new example, just find the 3 closest people on the scatter plot. And then whatever the majority class is among those 3 neighbors, that's what you would predict for this person. And then if K is like 5, then you would look at the 5 nearest neighbors and so on. So that's the basic breakdown of how a nearest neighbor classifier works. And typically you want K to be odd because if you had it even, like let's say K was 4, then you could have a situation where like 2 of them are 0, 2 of the neighbors are 0, 2 of the neighbors are 1. So that you don't really have like a decision to make there. So we usually use K as equal to some odd number. That way you always are guaranteed to have a majority amongst the neighbors. And then from that point on, it's quite simple actually. So it's just like whichever class shows up the most amongst my K nearest neighbors, that's going to be my prediction for this person. And so because of that dependency on the training set, like remember we talked about how your classifier is built on your sample data, your training set. That's what you use to like build a classifier from. So your training set's kind of that scatter plot that you're making these decisions based off of. And so if you have a new example come in, that example actually needs to be compared to the training set. In this case, you look at like the nearest neighbors within the training set. And then once you find the nearest neighbors, you can then make a prediction based on the majority class. So there's a lot of dependency there on the training set. And technically every machine learning algorithm actually has this property. Even linear regression technically depends on your training data. Like, if you're trying to predict some new individual, right, you're going to basically see where they are on the regression line. But how did you create that regression line? You created it using the training data, the sample data that you have. You created it from the specific correlation coefficient that you got, from your training data, the specific standard deviation of your X variable, the standard deviation of the Y variable. All those things were dependent on your sample training data. So that's the basic idea here is, you're technically like finding a way to compare a new example to your training data. And there's just different ways you can do that. Linear regression is one way to do it. If you're predicting something that's numerical, if you're predicting something that's categorical, nearest neighbors is another way to do that. That's the basic idea. And so we'll go over kind of a specific example today, which is going to be a slightly different data set from last time. And so this is going to be an actual like real world problem that happened. So this is a 17-year-old student back in 2012. And so she actually won this Google Science Fair competition. And the competition, the idea was to like build a breast cancer classifier. So take a bunch of data about some patients and then predict whether they have breast cancer or not. And so she built a classifier to do this, and she got 99% accuracy on like a test set that the model had not seen before. And so it's like quite accurate. And so this is her meeting President Obama at the time. So it's pretty cool. And so we're going to try to build something similar, but it's going to be a little bit simpler, but we're going to build a classifier to do the same exact thing. And so basically the way that the way this classifier worked was you get images of kind of cells in your body. And so basically like looking at tumors. And so on the left, you have like a benign tumor, on the left, or on the left, you have a benign tumor, on the right, you have a malignant tumor. And so the idea is to kind of predict what type of tumor it is based on this kind of image. And so we're not going to directly input this image into our classifier. The image has been simplified a little bit. So like some experts have come in, they've looked at this image and they've noted down like some numbers, some different properties, which are going to be the variables that we're actually going to use. So we're simplifying the data a little bit. We're not just taking like the pixels in the image or anything like that as our input here. But that's kind of the basic setup. And so we can take a look at kind of what the data actually looks like. So for today's demo, there's some cells that take a while to run. So rather than like run each one for you guys, I've already just run everything beforehand, but we'll just go through each one step by step, but I won't be like running any cells today. So this is actually what the data looks like. So it's called breastcancer.csv. We're just looking at the first 5 patients. And so again, these variables that you're seeing here across the top, the columns, these are created from the image by an expert, maybe like by a radiologist or something. And so these are just different variables here. So we have like clump thickness, uniformity of the cell size, uniformity of cell shape, and so on. So a bunch of different kind of properties about the cells that are in the image. And then at the very end, we have the class. So that's like whether it's this cancer cell or the tumor is malignant or not. So benign basically means like it's not like a very serious one. It's not like a cancer essentially. And so how do they know the class already? This is, again, this training set, this sample data is taken of patients where they observed, these kind of images, the scans of their cells, but they also observed whether they actually have cancer. So maybe they did some like additional tests, like additional blood work, like way more intensive tests than just like a scan of your cells. And that's how they were able to figure out whether they truly have breast cancer or not. And so the idea is, if you have a new patient coming in, the idea is you don't want to have to run through all those tests again. Is there a way that you can predict whether they have cancer using just these few properties about their cells? That's the whole point of it. So, again, limited information. Individuals in the future have limited information. You have to make a prediction based on that. So first of all, we can firstly just group our entire table just to get a sense of how many people are in each class. So it looks like we have 444 people with class 0, 239 with class 1. And this breakdown is actually, you've probably noticed kind of a pattern here. Like it's really often, really common where you have like the class you're kind of interested in, you don't have that many examples of that one. Whereas the one that you are less interested in, I guess, is typically more. And that's just a common thing that you'll see. And so one thing we can do here is, if you wanted to build a nearest neighbor classifier, let's say that we were only going to look at 2 variables. So here we're going to use bland chromatin and single epithelial cell size. Not sure exactly what all those things mean, but we're going to take a scatter plot of these 2, and then we'll just, similar to last time, visualize kind of the points and then also what the classes are. So you can see there's a bunch of points down here that have a class of 0, and then a bunch of points out here that are class of 1. And then if you start to get somewhere around here, you start to see this like kind of overlapping where it's like this like dark gold. So that's like the blue and the gold are on top of each other. So one question for you guys is, it looks like there's a lot of data points here. There's like 444 with 0 and then 239. But if you look at the scatter plot, this scatter plot doesn't seem like it's like several hundreds of points. So why do you guys think that might be the case? Any thoughts? Yeah, many points are overlapping. They're stacked on top of each other. And the reason for that is because these 2 variables, they're discrete. So discrete meaning that they don't just take on like infinitely many values. Like they're not going to take on float. They're not floats. They're integers basically. So you see here like this epithelial cell size, it goes from like 1, 2, 3, 4, 5, and so on. And then same for bland chromatin, 1, 2, 3, 4, 5, and so on. So they're discrete. So you're going to get a lot of points right on top of each other. So to visualize this a little bit more easily, what we can do is we can add some jitter. So what that means is we have all these points that we plotted on the scatter plot, but for every single point, let's just move it up or down by a little random amount. So if we do that, it makes it a little bit easier to visualize. So now this is the same scatter plot, but now you can see like kind of a better sense of how much data is there. So this isn't the actual data. We've like added some noise. but it makes it a little bit easier to visualize. So now you can see that we have a lot of blue points like around here, and then gold points are more like scattered around across like the entire scatter plot. And so, I mean, it's a little bit hard to see here, but if you assume that, like, let's say each of these was just like one point, like each of these two dots, these are like two different points, let's say. So if you wanted to do like a nearest neighbor classifier, what you could do is you could say, you first specify upfront what you want k to be. So let's say we want k to be equal to 3. And so if k is 3, if my cursor is like over here, I need to find the 3 closest points to this cursor. So these two seem like they'd be the closest to the point like out here, and then maybe one of these points out here as well. And then from those 3, you have to figure out like what's the majority class. So we already have 2 that are blue here, so it doesn't even matter really which one is the closer one in this cluster. The prediction would be blue for like my cursor out here, because that's the majority class of the 3 nearest neighbors. And then if I was like over here, let's say at 8 and 2, in that case, the 3 nearest neighbors would probably be these 2 guys, and then maybe again one of these clusters. But again, at that point, it doesn't really matter which one it is from here. There's already 2 other 3 are gold. So the prediction for somebody here would be gold. So that's kind of how a nearest neighbor classifier would work if you had 3 as your k value. And then if you increase k to like 5, you would just have to look at more neighbors. And so how would you decide like what value of k to do? The way you would do it is you'd first build a classifier assuming some value of k. Once you've built your classifier, then you run it on your test set to see how it performs, and you can get a sense of like how good it is on the test set, which test set means that it's data that has never been seen by the classifier before. And then you could repeat the same process with like k equals 5 or k equals 9 or whatever, and then just kind of compare the performance of all of them on the test set. And the one that does the best, that's the one you should actually pick, because that's probably the one that's going to work the best for new examples that come in the future. So that's like roughly how you would choose what value of k to go about. And again, k is just the number of neighbors you're going to look at when you're making a decision. So if k equals 3, that means that if my cursor is here, in order to determine what my prediction is for this person at 8 and 2, I would just find the 3 closest people on the scatter plot to that point. And then whatever the majority, whichever one comes up the most amongst those 3 people, whether it's 0 or 1, that's my prediction. That's pretty much it. Someone said closest on the left or the right. It doesn't matter. It's just closest in general. So like if there's a dot here, right? Looks like this yellow dot up here is probably the closest one. And then the second closest is maybe like that dot to this point. And then third closest might be like a point over here. So it's just kind of draw a line out to like all the points. The closest ones are going to be the ones that have like the shortest line to your point. Cool. So that's kind of how we would do it if we had 2 variables. Now we talked about last time how sometimes 2 variables, like it's great, but it might be useful to go look at things in additional variables, right? We had that example where like you had these things that were like overlapping, and so look like there's not much separation between the 2, but then if you like look from the side, there actually was separation between the 2. And that's because you looked at an additional axis, you looked at an additional variable. So if you look at additional variables, typically you'll be able to find separations more easily. And so that might be the case here as well. We're just looking at these 2 variables here, but maybe if we looked at a third variable, we'd find that these scatter plots, maybe they look like this right now, they would actually be like really nicely separated in like 3 dimensions or 4 dimensions. And so it's almost always going to be the case that that's going to work better in terms of finding a better separation. There's a limit. Like you don't want to just have like a million variables necessarily, because that's just like kind of a lot. But to a certain degree, having more variables will typically help a little bit. So the idea is if we are in like 3 dimensions, or let's say like 4 dimensions, right? We still need to, in order to run this classifier, we still need to figure out how close, what are the closest examples in the training set. And so we just saw how if you have just 2 variables, how close something is pretty easy. Just take your cursor and then draw a line to one of the points in the training set. The length of that line is how close that person is. But in 3 dimensions or 4 dimensions, it becomes hard to understand what does close really mean. So we can actually define it mathematically, and that's kind of how we'll do it. So we'll just define it mathematically, and then it's going to scale up to the additional dimensions as well. So So here's distance. We'll go over this right now. So in 2 dimensions, this is how you calculate distance. So if you have some point x0, y0, and then you're trying to find the distance to another point, x1, y1. So again, in the analogy of what we just did with the scatter plot, imagine that x0, y0 is my cursor, and then x1, y1 is an example in the training set. So if I want to find the distance between those two, we just use the Pythagorean theorem. So it's pretty much just, the difference in the x values, take that difference, square it, then take the difference in the y values, square that, add those squared things together, and then take the square root. So that gives you kind of the hypotenuse to this triangle. And so that's actually the distance. That's the length of the line between any 2 points. So that's how we can define the distance when you're talking about just 2 variables. So in this case, the 2 variables are x and y. So we observe these 2 variables for both of those things. Now, it's a good Key and Peele reference. Now, if you want the distance between 2 points, this is how we do it if you have 2 attributes. But if you have 3 attributes, how would you do it, right? So if you had 3 attributes, here's how you could do that. So you could have the same type of formula applies there. You just add your additional variable there. That's pretty much it. So like you do x0 minus x1 squared, y0 minus y1 squared, and then z0 minus z1 squared, and then take the square root of that. So that's how it scales up to 3 dimensions. And that's pretty much how it's going to work in higher dimensions as well. So it's actually quite simple. You just keep adding the differences between every single attribute. So you have like, if you're looking at 2 different individuals, it doesn't matter how many variables you're looking at, just look at the difference between each of the variables. So just have the differences of each of the variables separately, square those differences up, add them together, and then take the square root. And then that's the distance. So any questions about that before we continue? Okay, cool. So let's make a function to calculate distances. So here we have a function at the bottom. And so we're going to create this function that's going to basically just do what I just showed you in the formula. And it's going to do it on 2 arrays because we're going to assume that we have like all the attributes of our individuals in arrays. So arrays meaning like each entry in the array is like a different attribute about them. And so if we have like all the attributes of one patient and all the attributes of another patient or a point, and we want to know the distance between them, what do? Well, we just subtract kind of each of the attributes values between the two, then square all of them, then add them up, and then square root. So how can we do this in code? Well, with arrays, it's really easy because you can just take an entire array and like subtract another array. So that's the first step here. So take the first point, subtract the second point. So now that gives like all the subtractions between the attributes. Then we square it. So once you have that the subtraction between the 2 arrays, you have this new array. You can just square that. That's going to square each element of the array. And then just sum up all the values of the array. And then finally, once you have the sum of all the kind of squared differences, then you just square root the sum. And that's going to give you the distance between 2 arrays. So we're just basically applying that formula here, but using Python to do that. Good question. Someone said, does the order in which you subtract matter? It actually doesn't. So you could do 0.2 minus 0.1 and then square it. Because you're squaring it, it actually doesn't matter. So, if 0.1 minus 0.2 is like 5, that means the other way around would be negative 5. So 5 squared is 25, negative 5 squared also 25. So it doesn't matter. Cool. So this is how we actually calculate the distance between 2 arrays. And then in our particular case, when we're looking at data, we're going to have our data in row format. So like every row is going to be a different individual in our data set. And so we want to be able to subtract like 2 different rows because that's how we would calculate distance between 2 individuals in our data set. So we'll create another function which just does it expecting rows rather than arrays. And so it's going to use a distance function, but basically all we'll do here is the row distance is just going to take row 1 and row 2. It's just going to convert them into arrays each. So convert, convert row 1 into an array, convert row 2 into an array, and then pass those array into the distance function that we just created up above. So that's all we're doing here. We're just kind of convert the rows into arrays and then use the distance function. And so once we have that, we can actually start using this function. So firstly, let's take a look at our data set again, and let's just look at the first 3 examples. And so here we're going to drop the class column, because when we're calculating the distance between any 2 people in our data set, we need to assume we don't know the class. We don't want the class to contribute to the distance. You want the distance to be just between like the attributes that we're using to predict the class. So it's really important that we drop the class. And then so now if we just drop the class, we just have these variables here. And then if you wanted to know the distance, let's say we wanted to know the distance between like patient 0 and patient 1, we can now just use our function to do this. So we can do row distance, and then we have our table, which we're now calling attributes. So we can do attributes.row 0, attributes.row 1. And so in this case, the distance between them is 11.87. Now, what does 11.87 mean? It's kind of hard to really interpret this. I mean, there's no units attached to this. Like all of these variables have their own units. So this value on its own like really doesn't mean anything. But the idea is, right, when you're doing nearest neighbors, you're just trying to find the, like k closest neighbors. So all that matters is like, is this distance relative? Like, if I can say that patient 0 is closer to patient 1 than like patient 3, that's all I need to be able to do, really. And so you don't really need to go to interpret these units on their own. This number on its own doesn't really mean anything, but we can just compare it to other values. So for example, let's see how close patient 0 is to patient 2. So in that case, the closeness is 2.23. So patient 0 is much closer to patient 2 than they are to patient 1. So now we have a way to kind of compare distances, basically. And then the other interesting thing about distance, of course, is that if you take patient 2 and compare it to themselves, that's just going to be 0, because all the attributes minus the same value, you're just going to get zeros throughout the whole thing. So this is something you should expect to see. If you don't get this with your distance formula, there's something wrong there. So that's really important. And then someone said, does this mean we're doing distance in 8 dimensions? We're actually doing distance in 10 dimensions, it looks like. Oh, wait, 9. I'm counting wrong. Yeah, 9. So we have 9 variables here. So we're actually calculating distance in 9 dimensions now. So it's like impossible to visualize, basically. But at least we can mathematically do it, and that's all that matters here. Mathematically, we can say like these things are closer to each other, even though we can't like visualize it in a scatter plot or anything like that. So also to clarify, we haven't chosen k yet. We haven't done any nearest neighbor yet. All we've done is how can we calculate what is near and what is far. That's all we're doing right now. So it's just the first step of it. So now let's actually figure out how do we find the nearest neighbors. So we know how to figure out who's near and who's far. Now to figure out who's the nearest and how many of the nearest do we care about. And before we do that, there's going to be some things we're going to do with the rows that we haven't done yet. So this is probably the last time ever in this class that we'll go over something new in Python. And it's not going to be that new, but it's just good to kind of go over this before we use it. So our table has a bunch of rows. Each row is corresponding to like an individual or a patient. And so these are just some functions that we're going to use. So firstly, we have, if you have your table as t, if you do t.row I, that just returns the ith row of your table. So we've seen this before. And then if you have your ith row, you can then look at the j column within the ith row. So that means is if I take patient I, let's say I want to look at like a particular attribute. Right now we were just looking at 9 attributes. Let's say I want to look at like attribute 7 or something like that. So this is how I could do that. So you take the row of the person and then take the item. The item will just return like a specific attribute of a specific person in your data set. So that's that function. And then the other nice thing is if all the values of your row are numbers, then if you just pass in the entire row into np.array, it converts it into an array of numbers. So that's what we just did with that distance function. So we had the distance function, and then we created that row distance, which converted each row into an array. So the reason we could do that is because all of the attributes were numerical. If any of them were like categorical, like let's say there's a variable on like what city the patient lives in, that would have messed up everything. So it's really important that like all the attributes that you care about are numerical. If you have some that aren't numerical, you can just drop those columns out before you try to calculate the distance. So that's really important. That will happen sometimes, in your kind of actual work. So it's good to keep in mind. Oh, this isn't moving. Sorry. And then another thing that's really cool about rows is that you can use for loops really easily with them. So you can write for loops like this. You can say for row in t dot rows. And what's going to happen is for each iteration of the for loop, row is going to be assigned to kind of the next row in the data set. So instead of doing like for I and like np.arange t.num rows or anything like that, you can just directly write this out. So it's just a much cleaner way of writing for loops, basically. So rows kind of work nicely in that sense. So we'll see an example of this. And then lastly, we have t.exclude. So we just actually just use that. So exclude, or actually, no, we didn't use this yet, sorry. T.exclude is different than drop. So drop is like for removing a column from a table. Exclude is for removing a row from a table. So this will return the entire table without the ith row. And the reason we're going to do this, you'll see an example of why we're going to do this. Actually, I won't explain it right now, but this is like probably the least used one, but there's some situations where you might want to use it. There's a reason you might want to take out a patient from your entire set of individuals. Cool. How do you know the index of a row in a big data set? So there's ways we can do that. We'll actually see some examples right now where we like there's a specific row that we want to take out, and we know how to do that. Okay, cool. So now that we have those functions, I wouldn't worry too much about these right now. We're going to go over them and I'll explain them when we go over them again. But now we're going to actually build our nearest neighbor classifier. So here's how the algorithm is going to work. Finding the k nearest neighbors. So we'll just go over this in steps. So to find the k nearest neighbors of an example, again, you have some new example who's come in. You need to find the k nearest neighbors from your training data. How do you do that? First of all, you need to find the distance between the example and every single point in the training set. So imagine that scatter plot that we had. When I had my cursor there, we actually need to calculate distance to all of the points in the training set. Because visually, for us, it's easy to tell like what's the closest. But for a computer algorithm, like it needs to actually do this math. So you need to calculate distance to every single point in the training set. Even somebody who's like really obviously far away visually, you still have to do that. So that's what the computer needs to do. Calculate distance to every single point in the training set. Once you've done that, we're going to take our training data table with all the rows of individuals and then add a new column which just contains the distance. And that's kind of the distance of that individual to the example that we're trying to predict on. So we're going to have all these distances for all of our individuals in the training set. Once we have the distances, we can then sort our table based on how far they are to the example. And then now that we have them sorted, we simply need to take the k rows of the table. So take the top k rows of that sorted table. Now we have the examples that are the k nearest neighbors. And then once you have the k nearest neighbors, then to actually classify, what you do is take the majority vote. So you have your k nearest neighbors now. All you need to do is look at their class and then see which class shows up the most. What's the most frequently occurring class amongst those k neighbors? And then whatever your majority class is, that's what you assign to the new individual that you're trying to predict on. So that's basically how it works. So any questions about that process? Someone said, what if 49 are 0 and 51 are 1? So in that case, that means your number of neighbors is 100. So you typically want to choose your number of neighbors as odd. It's usually like a good idea. So then you'll never have like a tie, essentially. I guess you could still have a case where like you just have slightly more ones than slightly more zeros. It is close, but I mean, if you had to make a decision, like you probably would pick the one that's a little bit, more often or occurring more often. Seeing a lot of questions about standardization. So we'll go over that at the end of the lecture, but in general, it is a good idea to standardize all of your columns of your table. And I'll go over that why that is the case. There's some cool examples of that at the end of the lecture. Cool, so let's actually go through and build the classifier. Sorry, I don't know why this is happening. Okay. So first of all, we're gonna do the first step, which is I have my training data, I have my example. Let's compute the distance between the example to every row in the training data. So that's what this function is going to do. That's all it's going to do, distances. So it's going to make an array here called distances. And then we're going to take our training data and drop the class column, because again, we don't want to use the class column. We don't know the class for this new example. So we don't want to keep it around right now. So we're going to create this new table, which is just the attributes. And then what we're going to do is for each row in the attributes only table, we're going to just compute the distance between that row and the example. So that's what we're doing here, row distance between the row and the example. Once you had that distance, just append it to the distances array. So that's all we're doing there. And then I put a note here that this, these two lines here is equivalent to writing it like this. You could have also written it as for I and np.arange attributes.numRows, and then row equals attributes.row I. So you could have done that, but this just allows you to do that in like fewer lines of code, and it's a little bit easier to read actually, I think. So that's what we do there. And then finally, once you have all your distances for every single example in your training set, we're going to return a new table. So the new table is going to be our training set with a column that has distance to the example. So that column is going to contain all the distances of each person in our training set to the example that we're trying to predict on. And so we can see an example of running this. So let's say we chose like row 21. So let's say we have a patient at 21 or 21st patient. Let's see what the distance is of everybody to the 21st patient. And so we can actually use a distances function to do this. So here we're going to use a distances function. We're going to pass in all of our patients excluding the 21st one, because we already know the 21st one is obviously going to be the closest to the 21st. So let's just remove the 21st patient. So let's just imagine that like we don't know anything. We don't know the class of the 21st patient. Let's take them out of the table and then calculate the distances of everybody else to that 21st patient. Once you have the distances, we'll then sort by that distances column that's going to be created, because that's what we ultimately want to do. Is why are we calculating distances? It's so that we can sort them and find the closest ones. So this is what that table looks like here. So you have all the attributes of everybody, then you also have the class of everybody, and then finally you have the distance. So that's that last column here. So now we have the distances to everybody. And so then at this point, it's like you have to choose a value of k, and then whatever the value of k is, that's how many rows we're going to just keep from this table now that we've sorted it. So why did we drop 21? We dropped 21 because we wanted to see the distance of everybody else to patient 21. We wanted to imagine that like patient 21 is a new person who's come in and whose attributes or whose class we don't know yet. And so we wanted to just pretend that we didn't know anything about that person. That's why we took them out of the table. So that's why we did that. So now we have kind of everybody in the training set, and we know like how far they are to this point, to patient 21. So now that we have that, the next step is to find the closest ones. So let's make another function that's going to return the closest points in the training set to our example. So here we're just going to call it closest. It's going to take in our training set, the example that we want to predict on, and then k. So k is how many neighbors to consider when you're making that decision. And then here's how it's going to work. So first of all, calculate the distances between the example and everybody in the training set. So we're just going to use that function again. Then sort by the distances. So that's exactly what we just did above. And then finally, once you have your table with your distances and it's sorted, lastly, we're going to take the first k rows. That's what this thing does here. So take np.arange k. So take row 0, 1, 2, 3, up to k. That's what that means. Up to, but not including k. So this is just a generic function that's going to work. And then how are we going to use it? So we're going to use it using the way that we just did above. We're going to pass in patients.exclude 21. That's going to be our training set. And then example is going to be what we already assigned example to patient 21. And then we're going to use k as 5. So I'm just picking a random number here. We're going to pick 5, see what happens. And so now if you run this, function, we get the exact same table as what we just saw above, except we just have the first 5 rows. So this function just basically does that for us. It like does all the things for us, like calculate distances, sort it, take the first 5. So it's doing like all of those things for us. So here's what we get. So now we know these are the 5 closest neighbors. So you guys should be able to tell right away, if we have this as our class column, what's our prediction going to be? for patient 21 based on the 5 closest neighbors. Yeah, so it's going to be 1 because 4 of the neighbors are 1, and then only 1 of the neighbors is 0. So the majority is 1 in this case. So this is how we would make our prediction. And so if we want to just add a couple more things to just make this a little bit easier, so visually looking at it, if we could just make the algorithm return that number. I want Python to just return 0 or 1 for me, rather than me having to look at this table. So we're going to do a couple more steps to just get that done. So if we have our closest, if you run our closest, which gives us, this table up here, then what we can do is we can group by class. So if you group by class, that's going to give us kind of the number of times 0 and 1 show up. And then once you have that table, that group table, you can sort that table by the count. So you sort it by count, descending equals true. That's going to put the majority one on the first row. So it's going to make sure that the majority class is at the top here. So that's all we're doing here. So it's a little bit convoluted, but we're doing this so that we can just make sure that the majority class is on top when you group. Because if I group without this, then it's not going to work. If I group without this, I'm going to, by default, these are just ordered like in increasing order. So that's kind of why we do that. We do the sort. So if we sort it by count, we just make sure the one that comes up the most is up at the top. Cool. So now that we have this, we can finally create a function that returns the majority class from the top k. So if I know what the top k are, if I know what the top k neighbors are, I'm just going to basically plug in top k with everything that we wrote to the right here. So I'm just taking everything to the right here and then pasting it down here. So take your top k, group it by class, then sort that groups table by count, and then finally take column 0, which is going to be the class column, and then take item 0. So item 0 is going to be this. So this will give us the top left entry in this table, which is exactly what we wanted. That's the prediction. So that's all this is doing here. So if once you have your top k neighbors, this function is going to return that class that shows up the most. So now that we have that, we can finally put it all together into one function called classifier. So this is a function that you would actually use when, this is kind of like the final function. I was just showing you all the pieces to it. So the final function is classify, takes in a training set table, takes in an example that you want to predict on, and then takes in k, the number of neighbors. How does it work? It takes the majority class from the closest k examples. So again, closest, this function returns the k closest examples. Once we have those, just pass that into the majority class function. That's going to find the majority class amongst the k closest people. So we're just kind of putting all those functions we've created together. And now this function's like really nice, and it's like just a one line of code basically. And so now we can actually apply it on our patient 21. So we can run classify. Again, our training set is going to be the patients without 21. Our example is patient 21, and then we're going to use k equals 5. So in this particular case, we get 1. That's exactly what we expected based on what we saw in the table above. 1 was the majority class amongst the 5 nearest. Sorry, I don't know, my internet's unstable. I'm good now? Okay, let me repeat that. Where did I get cut off? Did you guys hear me talk about the majority class? Okay, line 23. Okay, so once we have our classify function, beginning of lecture. Once we have our classify function, we can now run this on any new example. And so firstly, let's just verify that it works on patient 21. So we're going to take classify, pass in patients.exclude 21, pass in example, and then k equals 5. So we get a prediction of 1, which is exactly what we expected based on the table that we saw just above here. So the table up here, if I go up to the top, the table here had 4 of the neighbors were 1, and then 1 of the neighbors was 0. So we already knew from visually that this prediction was going to be 1, but now we're just verifying that it works. And then now that we predicted 1, let's actually verify what the actual value was. Because remember, this whole exercise, we pretended that we didn't know what patient 21 had, but we actually do know that. So we can actually check we can kind of look behind the curtain and see what the actual value is. So the actual value, in this case, I'm just going to look at the entire patient, is 1. So it looks like we actually got it right. So it works but it works for that one person. So, you don't really know if it's like the best algorithm in the world, but it does work for that person. And so we can try this again. So now let's take maybe patient 10. So let's create a new example, patient 10. Let's do the same thing. So let's classify using patients except for patient 10. And then look at the 5 closest. In this case, prediction is 0. Now let's look at patient 10, and they actually are 0. So it's correct again. And we can do it again with like patient 15. Prediction is 0. Let's look at patient 15. In this case, actually the prediction, or the actual value is 1. So the prediction was wrong in this case. So this just shows you the prediction is not perfect, but does a pretty decent job. So this is actually an actual classifier. And so just a review of the steps. Basically, first we created this distance function, which allows us to take the distance between any 2 arrays. Then we said, well, our data is actually in row format. So let's just create a function called row distance, which will basically just return the distance between 2 rows. Okay, now we know how to create the distance between any 2 rows. Let's create a distances function that calculates the distance between any row in our training set and a new example. And so that's what distances does. And actually calculates the distance between the example and every single row in the table. Once you have all the distances, everybody in the table, let's then sort that table and find the k closest people. So like sort that table and then just take the top k neighbors. Once you have the k closest neighbors, we create a majority class function, which just returns the single prediction, which is the class that shows up the most amongst those. Man, sorry, I keep getting cut off here. Yeah, so distances is, once we know how to calculate distance between any 2 rows, distances allows us to calculate the distance between the example and like every single row in the training set. And then once we have all the distances, then we can sort that table. That's what closest does. It sorts the table and then finds the k closest. Once you do that, you just pass it into the majority class. And then majority class returns a single prediction, the class that showed up the most amongst the k nearest neighbors. And then we just put that all together into our classify function. So classify function just kind of wraps it all together. But that's just kind of a breakdown of the steps here. And so this is exactly how a nearest neighbor classifier would work. And so we chose k equals 5. You're going to have a different classifier with different values of k. So that's the important thing here. So any questions before I continue? What's the test set in this case? So we haven't even gone to the test set yet. Actually, we're not quite there yet. All we've been doing here is training the classifier. This whole process is like training the classifier. So the training part only looks at the training data. We haven't looked at the test set yet. I'm going to get there. And someone asked about the majority class function. So the majority class function takes your top k neighbors, it groups them by class, then it sorts by the count, then it takes the first column, which is a class, and then takes item 0. So, can I show line 44? Wait, I'm not sure what 44 is. Oh, right here. Yeah, this is just kind of taking our 5 nearest neighbors, then grouping that table by class. So that's going to return your like unique values of 0 and 1, how many there are. Then it's going to sort that table by the count. So by default, this table has 0 first and then 1. So we're just going to sort by the count because we want the one on top. We want the one on top to be the one that's like the most common one. So that's all we're doing here. Like sort by the unique value that's like the most common. That's all this is doing. Okay, cool. So now let's go on. So we have our classifier now. And then lastly, now that you've built the classifier, we specifically did like with k equals 5. We could have done that same exercise with like k equals something else. Then we need to evaluate the classifier. So now we know how to run like our classifier on any particular example. We need to actually evaluate this on our entire test set. That's how we actually validate how good it is. And so the accuracy of our classifier in general, it's going to be the proportion of examples that are labeled correctly. So if I have like a bunch of new examples come in, how often does the classifier get it right? That's the accuracy of this classifier on the population. So ideally, we'd like to be able to run this classifier on the entire population of all patients and then see what the accuracy is. Because, for example, with like a vaccine, right? Like if you want to know how effective a vaccine is, you'd ideally like to be able to do it on the entire population. But you can't do that right up front. So what you do is you sample some people and then evaluate the accuracy on them. That's essentially what we're going to do here. Um, so what we're going to do is, if our labeled data set is sampled at random from the population, that means we can infer the accuracy on the population using our sample. That's the basic idea here. And so what we're going to do is we have our sample, we split it into a training set and a test set. We use the training set to build our classifier, and then we use the test set to evaluate the classifier. So that's the only thing the test set is used for, is for evaluating the classifier. And we don't evaluate the classifier on the training set because it's kind of like cheating. Like the training set, we already knew everybody's outcome, and like we use the training set's attributes to create the classifier. So it's kind of cheating if you just use the training set. It is like a good metric to look at the accuracy on the training set. Like that is a useful thing, but ultimately the accuracy on a test set's going to be even better because it's going to allow you to see how it works on data that the model has not seen at all. And that's ultimately what is going to happen now when you go use it in the real world. So it's a better indication of how it's going to work on the entire population. So let's actually do this in code. So we just have a few minutes here, but we'll go over this. So firstly, let's build a brand new classifier. It's going to be different than the one above slightly because we're going to use different rows. We're going to use only specific rows here. So the entire table has 683 rows. What we're going to do is, firstly, we're going to just randomly shuffle our data. So sample with replacement, we've done this before. So shuffle our entire table. And then what we're going to do is the first 342 rows, that's going to be our training set. So once you've shuffled the data, the first 342, that's our training set. And the rest of the data is our test set. So that's how we're going to split it. So I just kind of made that up, but that's just how I did it. And then once we've shuffled our data into the training set and the test set, now we need to evaluate the accuracy. So here's a function that allows us to do this. So this evaluate accuracy function takes in our training set, takes in our test set, and it takes in a value of k, because the evaluation is going to depend on what k you choose. And so here's how it's actually going to work. So first of all, we're going to take the attributes of just our test set and just store that into test attributes. So we're going to like ignore that we actually know the class. And then what we're going to do is, for each row in the test set, we're going to classify what the value is. So we're going to run the classifier on each row in the test set and see what the model would predict. So that's what's happening here. So here we're taking classify, we're using training, passing in training data, and then the test example, row I, and then whatever value of k we chose. Once we have our classification, our prediction for that person in the test set, we're just going to count increments whether we got it right or not. So this is a variable here called num correct. It starts at 0, and then we're just going to add whether we got this particular person correct or not. So this will basically, this thing here is going to equal 1 if we got them correct. It's going to equal 0 if we didn't get them correct. So this is just a way to kind of like count up how many times we got the classification correct. And then once we have how many we got correct in our entire test set, then all we do is we return the number that we got correct divided by the number of rows in the test set. This gives us a percentage of how well we did on the test set. So that's basically all this function does here. And so if we want to actually evaluate it, we can try it out here. So if we evaluate the accuracy using our training set and our test set with k equals 5, we get an accuracy of 96%. So this particular classifier, if you choose 5 nearest neighbors, you get an accuracy of 96.5% when you predict on the test set. If you did k equals 3, you actually get a higher accuracy. So using fewer neighbors is actually better. So in this case, we get 97%. And then also, if you use 11 nearest neighbors, you get a classification accuracy of 97% as well. So it's kind of interesting, but you can see how it varies based on what k equals. And then what if you just use the single nearest neighbor? Well, you actually still do a pretty decent job. So if you use the single nearest neighbor, you get 95% test accuracy. So also not that bad. And so, I mean, in the actual competition, the winner got 99%. So like we're pretty close here just using 2 variables basically, which is like, or not using 2 variables, sorry, we used 9 variables. And we just used like nearest neighbors. So it's pretty impressive that we got like pretty close already, just using nearest neighbors. This is pretty cool to show you how good it can be. But in general, one thing to keep in mind here is all 4 of these, they're using the same number of variables. They're all using 9 variables. The only difference here is how many neighbors are you looking at. That's the difference here. So this is looking at 5 nearest neighbors amongst, but nearest is defined as, remember, that like distance between those 9 variables. But just like how many distances do you look at? Do you look at like 5 closest? Do you look at 3 closest, 11 closest? So that's just looking at how many people do you look at. But the number of variables that's compared when you make that distance is the same. They're all using 9 variables. So that's just really important here. And so this is basically how we can actually calculate the differences here. So we're over time. I did want to go over the standardization stuff, but I'll go over that in the next lecture because we do have some time in the next lecture. But I think I'm going to stop there. But if there's any questions, happy to kind of go back over the notebook or review anything.